Okay, so this is the second video from arc length, section 7.4 in the book. I hope you find these examples beneficial. I'll do several since class was such a debacle yesterday with my, I don't know what you call it, algebraic breakdown or something. So don't let this section intimidate you. Okay, so I thought the first example we should look at is just number 8. I just picked one. I thought that this one illustrated the kind of stuff that you might need on several of yours. So anyway, we've got y equals 1.5 x to the 2/3 power plus 4, and we're supposed to find the arc length from 1 to 27. So I thought we should just picture that first. So let me grab my drawing. Okay, so you can see that here's about 1 to 27, from 1 to a little more than 27, and here's that function. So you can see that the arc length probably is like 30 or 40 or 25, something like that. It's going to be fairly significant arc length on this guy. Okay? It was a straight line. It looks like it'd be about 30 or so, or maybe 25. I'm not sure. But anyway, there's the picture. So let's put that away. All right, so the arc length, remember, is from 1 to 27, and it's going to be the square root of 1 plus the derivative squared. Remember, you want to be real careful about that derivative if you're doing dy dx or dx dy. We're going on an x interval here, so we're doing dy dx, and that's generally what you're going to do. You might have a couple that you do dx dy on, though. Anyway, so we set up the arc length. Remember, that's called s. We go from 1 to 27 in the integral. And there's our square root. It's always nice to take the derivative first, so you can see that they already took the derivative over here. That's a pretty easy derivative, right? The 4 just drops out, 2/3 times 3/2 is gone, and negative 1/3 is left. If it doesn't come out so nice right away on that one, you should probably make sure that you try to simplify it as much as possible. The more you simplify this, the probably easier your arc length calculation is going to be. Okay, so anyway, the arc length, we've got the integral from 1 to 27 going. All right, so let's just square that and maybe make a common denominator. That's probably a good idea. Remember, the idea on most of these arc length problems is to eventually get rid of that square root somehow. So you're trying to get everything inside to be squared so that you can get rid of the square root. So that's kind of the strategy you might pursue. Anyway, so we're going to have the square root, and sorry if my writing's a little sloppy, it's hard to write with the mouse. So we're going to have 1 plus 1 over x to the 2/3, right? Then we can make a common denominator. We're going to have 1, common denominator, not 1. Common denominator is going to be x to the 2/3, right? So it's going to be x, whoa, that's a crazy x, to the 2/3 plus 1 over x to the 2/3. And at this point, remember, we're trying to get stuff outside of the square root. So this x to the 2/3 is all by itself on the bottom. So think about what that really means. It helped me to rewrite it in terms of its root notation. So let me rewrite that for you. So I rewrote this as, well, let's not go root notation. Let's just say that that's x to the 1/3, right, squared. That's the same thing as x to the 2/3. Now, why did I do it that way? Well, now because square root and that squared cancel, and now this guy can pop outside. Okay, so now that guy pops outside. He's not outside the integral, but he's outside the radical. So it's 1 over x to the 1/3 outside the radical. So we've accomplished some of what we needed, and what's left inside is x to the 2/3. My computer is really loud here. Sorry about that. X to the 2/3 plus 1. I've been forgetting my dx all along. So let's get it back in there. So now maybe this kind of looks like a u-sub problem, doesn't it? To me it does. I see that there's something inside and something outside that are pretty similar. So I'm just going to try a u-sub at this point, and that's what you might do. It looks like this could be u-subbable, so I'm going to just make u the inside and see what happens. So if u is that, then the derivative, du, or differential I should say, is going to be what? Just like up at the beginning when we did it, it's going to be x to the negative 1/3, isn't it? And then when we bring that 2/3 down, and then 1 goes away, right? Dx. So if you think about that, x to the negative 1/3, hey, it's right out there. So this definitely is going to work in terms of a u sub. So let's just finish it. We can go 3 du, move that 2/3 over. 3/2 du now is equal to dx over x to the 1/3. And now we can just sub this stuff right in. There's our x to the 1/3. And so we can just sub right in, and we should be golden. So actually, you know what? I'm not going to write equals because I don't want to change the integrand. I guess we could. Maybe we should. Let's just change the integrand on this one. You know what? Let's put equals. So we'll think about what 1 and 27 become here in a second. Anyway, so this part, well, I should say this part and this part are 3/2 du, right? So let's pull that 3/2 outside. And what we're left with is root u du. And let's think about these were both x's. So what are those going to be now in terms of u? So this is going to be u equals, what if we put 1? 1 to any power is 1, so that's going to be 2, right? If we put 27 into the 2/3 power, remember, let's do some scratch work over here. 27 to the 2/3 is the same thing as the cube root of 27 squared. We can put that squared inside or outside, right? So the cube root of 27 is 3, squared is 9. So we get a 9 up here now. Okay, so that should be a pretty easy integral to finish. So we get 1.5. Integral of root u is going to be what? That's u to the 1/2. So that's going to be u to the 3/2 divided by 3/2. I'm going decimals here, right? And then we're evaluating it from 2 to 9. So we have some nice cancellation that occurs there. And we get u is x to the 2/3, right? So let's stick this in our calculator. Let's see what we come up with. Well, I guess we don't even need, we changed the integrand, so we don't even have to go back to normal. Sorry about that. So it's going to be 9 to the 3/2 minus 2 to the 3/2, and I'm just going to stick that in my calculator. You could do it like we did up here in red, though, right? So I didn't think that was going to be like a super huge number. It's crazy when you get like fractional or decimal exponents, though. So it did turn out to be a pretty big number, actually. It turned out to be 24.172. That's a little smaller than I was expecting, but it's not out of the ballpark. And we should probably put units there because remember, this is arc length, not an area or volume. Okay, let's look at another problem. And this one I think we did in class, but we had some issues with it, so again, apologize about that. Let's see what it turns out to today. So we had this function that we saw last time, right? And it said evaluate it on the interval 1 to 1/2 to 2, and I think we pictured it in our calculator, and there was like another piece down here. But this is the piece we're interested in, right? This arc length from about 1/2 to 2 on that function. So first we take the derivative, right, and we try to simplify it. So the derivative of x to the 3rd is 3x squared over 6. That reduces to 1/2. And this guy is really, just this part is going to be 1/2 x to the negative 2, x to the negative 1. So the derivative is x to the negative 2. And it makes it negative. Right, and it looks like they factored out a 1/2. That's kind of just what we did in class. So you try to clean it up as much as you can before you stick it into the arc length formulation. Now, let's remember, our goal is to get the inside of this guy to be all squared. So somehow we got to get that 1 inside the squared. So if we keep that in mind the whole time, I don't think this is going to be too bad of a process. There might be one tricky step in algebra on some of your problems. Like last time, we had to factor out that x to the 2/3 on the bottom, right? Let's see what we have to do this time to get that to happen. So first of all, we plug in our stuff right here. And then let's just square it out. So this step is a little bit mysterious, so let's show it up here. So we're going to have, let's just show the inside of the root. So we're going to have 1 plus, what do we have there? It's going to be, when we square it, we're going to get 1/4, right? So 1/2 squared is 1/4, and then square this out. So you can use your little binomial formula. So it's going to be the first thing squared, sorry about my handwriting, minus 2 of the first thing times the last thing, and then plus the last thing squared. It's getting crazy. Hold on to your hat. Okay, so we've got that. That's still not down here, right? But if you think about this, these x squareds right here cancel now. And we have our 1/4 x to the 4th. That's right there, right? Our 1/4 x to the 4th down there. We've got that. So why does this become plus 2? Well, think about distributing this 1/4 in there. 1/4 times -2 is going to be -1/2. And then outside, right here, we have 1. So it's 1 minus 1/2. That's going to be a positive 1/2. And then if we want that positive 1/2 to go back inside the 1/4, to have a fourth denominator, you're going to have to go times 2 times 2, so it's positive 2. Can you see that up there? That's where your positive 2 came from. Okay, so let's get rid of some of this nasty handwriting. So we've got to this step. So let's try to take it a step further. Remember, our goal is to get this thing to look like squared, so the square root right here can cancel it out. So if you think about this guy, can we make that look like something squared? And the answer is yes. The next step is, there were 2 hard steps in this one, I would say. But a lot of your problems aren't going to have this many. So just ask yourself, how can I get that thing to be squared? And I remember in class a couple of you were saying things like, well, it looks like you could almost complete the square. Well, I think it is a perfect square. It's just a strange one. You know what I mean? Go back and look up here at what we did up here. Where did this part come from? This part right here, before we did the canceling of the x squareds and all that jazz, this part came from this guy right here, right? Expanding that guy, which was squared, expanding that guy out. The only reason we couldn't do it back then, like cancel the square root, was because of the 1 over here. So if you think about that, this guy is identical to this guy, except now this sign has changed to plus. So, in fact, this is already a perfect square. You don't even need to complete it, if you will. All you need to say is, well, let's just write down what we have. We have square root of 1/4. And then all that stuff in there, it's already a complete perfect square. It's the complete perfect square, x squared. And since that 2 is plus this time, it's plus 1 over x squared. Does that make sense? It's like the exact same problem we did here, except now once we've put that 2 inside essentially by what we did up here, now it's become like the same thing except with a plus. And now that whole thing is a perfect square. And now we have an integral that's not going to be bad. So it's going to go, I'm going to say 0.5. Easier for me to do 0.5 with this crazy mouse. Anyway, so the square root of 1/4 is 1/2. Square root of something squared is itself. And we can definitely do that integral. Okay, so I'm going to take the 1/2 outside and say the integral of x squared is x cubed over 3. Get a nice bracket on there. Integral of x to the -2 power is, plus. It's not plus, it's minus, right? Going to divide by -1, so it's going to be minus 1 over x. When we integrate that, watch your integral versus derivative. And we're going from 0.5 to 2. And I'm not going to try to do all this out, so let's see, what do you get? We get 33/16. So 33/16 is approximately, I mean the AP test wouldn't accept this of course, but it's approximately 2. Does that look like it might be an arc length of 2? Yeah, I think it does. Okay, let's do one more in this video, and then I'll do a couple more in another video if you feel you need them. So if you already were in class yesterday, we finished this one, so I thought I'd just do this for the future. Anyway, so this time we've got an implicitly defined function on an x interval, and we're supposed to find its arc length. So first, I think this one's implicitly defined. It might be easier to just do it in terms of y when it's implicitly defined. See, if you look at this, you can solve for x a lot easier than you can solve for y in this case. It's kind of up to you, though. I think this one might work either way. But anyway, just in case you need an x-defined one, let's do it that way. So here's what x looks like, right? And then you take the derivative, 3/2 comes down, y minus 1 to the 1/2. So that's no big deal. This time you can see that it became dx dy. So we're doing everything, the arc length in terms of a dy integral. So these x values up here, we've got to translate to y values. So you can do that with algebra or from looking at the curve. Looking at the curve, it looks like the y value of 0 is 1, the y value of 8 is 5. You could plug those in and solve for them just as easily. So we're going to go from 1 to 5. Okay, now we stick our derivative in. And this one, there's I don't think very much fancy algebra. Looks like when you square that out, the squared and the 1/2 cancel already. So then you get, let's do the inside there, 1 plus, what's this, 3/2 squared is 9/4, there's their 9/4, and then 9/4 y when you distribute it, minus 9/4. So do a common denominator, what's 1 minus 9/4? It's negative 5/4. Okay, so if you don't want to watch the rest of the details, I'd just go ahead and skip to the next video. But anyway, I don't think that's going to be very hard to integrate, right? We can just do a simple u sub. So let's go u equals the inside, 9/4 y minus 5/4. I think the book chose to like factor out that 1/4 and stuff. Maybe that would be easier, but I just see a u sub thing I can do right here, so I'm going to do it that way. Anyway, so then du is 9/4 dy, and you can flip that up. So then this guy becomes 4/9 integral root u du. So then this guy becomes 4/9 root u becomes 2/3. Oh, let's make that nicer. So times 2/3 square root of that stuff. I'm just going to say that stuff. It's not square root, my bad. So maybe the book's way was a little bit nicer on this one. But this will get the job done of the stuff to the 3/2. We're going to evaluate that from 1 to 5. Okay? So you do that, and you end up getting, no, I don't have my answer written down here, dang it. So let's see, we get 8/27, right? And on the inside, let's think about what we have. So when we plug 5 in, we're going to get 45, right? When we plug that 5 into this part, we're going to get 45 minus 5/4. Is that right? So that's 40/4. What's 40 divided by 4? 10. So that's going to be 10. And the part we missed in class, gosh darn it, is it's still to the 1.5 power, right? And then fundamental theorem, minus 1. 1 is going to be 9 minus 5. That's going to be, let's be careful. So when we plug in 1, we're going to get 9 minus 5/4. That's 4/4. That's just 1 to the 1.5. So that's just going to be 1. 1 to any power is 1, right? So then I'm going to put that in my calculator. this big. Okay, and I got about 9.073. Okay, so there you go. Hope that helped. I will have another video for those of you who are in class today, so make sure you watch that one. It's new.